We'll start with part 1 of color perception. In perception, a color is almost never seen as it really is, as it physically is. This quote from Joseph Albers tells us about how color is influenced by context. And he was an abstract artist who ended up teaching. And I'm going to a few times tell you that you have to believe me when I say that orange box at the top is reflecting the same exact wavelengths at the same exact level as that brown box at the bottom. And so what we're seeing, what we're experiencing is wavelengths. And actually, I'm going to end up saying that the perception of a color is the nervous system's interpretation of the wavelengths. And so when we say it's never seen as it really is, as it physically is, what we're doing is interpreting wavelengths. We're not seeing really the physicality in a way. And so they are so much influenced by context that when we think about how top-down processing works and how perception is filtered is different than the reality out there in the world, color is one of the best examples of that. So it's a perfect place to come back to talking about vision and the higher level, some of the higher level processes of vision. So I am going to make sort of a big deal about color perception being a psychological phenomenon, which I've already started doing. But again, what we're experiencing is electromagnetic energy and different wavelengths of that energy, and that's the physics. And our experience of color is the nervous system's interpretation of those wavelengths. And so there are some questions we can ask. One is, what does color do for us? And we'll talk about the functions early on. And these are questions I do plan to come back to, like I did in speech, so you can think about these and think about answering these. Another question is, what physical attributes of the object itself influence its perceived color? We can also ask what physical attributes of an object's environment influence its perceived color. We just looked at the Joseph Albers. Obviously, the environment has a huge influence, right? Those were the same wavelengths being reflected into our eyes, and yet we interpret them as being very different. And finally, how can we describe our color experience? And that's something you can think about doing for somebody who doesn't experience color vision. We sort of thought about this with music for someone who doesn't experience music, but maybe somebody who is blind, can't see, or just doesn't have color vision. How do you describe that to someone? And really, what is your experience? Because we all have different experiences with color. Some of us are very influenced emotionally. Some of us have those influences, but they're not as conscious, or we're not as influenced. I will say I usually start this in class by saying to my students, notice that I only wear black or khaki pants. I don't match things with things. I don't do color very well. I'll have a couple of jokes about my own color issues as we move through. Functions of color vision. One is beauty. So I have this Monet painting up there. I feel very lucky that I get to teach this class in the fall and in the spring. And I did steal this from the internet, and I don't know where I got it, but just so you know, we do have a very beautiful Monet here at the Columbia Museum of Art, and he used color amazingly. And I do get to teach about color right when things start flowering and blooming in the spring. I also teach about it in the fall, and so you can see maybe where I stole this picture from on the internet back before I gave people credit. I'm sorry, I did that for a couple of years when I first started here. I kind of forgot that I needed to do that, but so, and usually in class this is a nice time for me to ask people who are not from South Carolina, and especially people from New England. So what do you think about the falls here in South Carolina, and how do they compare, right? There's always this, you should be in New England for the fall at some point, and that it's still on my bucket list I grew up in West Virginia. We had a pretty striking fall in comparison to down here, but not as striking from what I hear as the New England fall. It's like Connecticut and Maine and places like that. I actually have learned to adore and love the South Carolina fall. We have a lot more green because we have so many pines, but then there will be these just flashes of red or yellow, and it's still, I think it's still very beautiful. The one function of color vision is beauty. Another is that it tells us, it helps us to identify and classify. When we talk about recognition, things being in their appropriate colors really helps us to identify them. And this is true for both man-made things and things from nature. And so this study from Tanaka and Presnell in 1999, they just had people recognize objects, and people recognized the carrots and the bananas and so forth. That looks like collards to me, but I think they named it something else like lettuce. They named them faster if they were in their appropriate colors than when they were in these off or different colors. Another function of color vision is identification of food sources. I mean, we're at identification, but one of the important things is being able to identify our food sources. This is actually what gave us trichromatic color vision, that this was evolutionarily adaptive, and there were monkeys that had a mutation where they had a third cone and they had this trichromacy, and it allowed them to see specifically the food that was relevant for them. So for certain monkeys, it was the ripe bamboo that kind of popped out from the background. But so if you think about something like picking berries, and these look like red berries, but they look like they could turn into blackberries. I don't know if you ever picked blackberries, but they have prickers. I don't know if these have prickers. I can't tell in this picture, but with trichromacy, we can go for the color. If we look at someone who's monochromatic, so this comes from someone who is a vision scientist and is monochromatic. So tri meaning three, we have 3 cones, and it gives us this range of colors. Monochromatic, those people either have only one kind of cone, or they're just they have no cones, and they're dealing just with their rod system. So they're just using their rods to see. But you can see that now, if those bushes have prickers or they're picking blackberries, there's no kind of pop out or distinction, and so it's more feeling around to feel for the berry, because you can't really pick it out based. I mean, the color helps us to see it, identify it, and helps it to pop out from the background. Another thing we do in color vision that is really nice is we go back to the stimulus and we talk about it and repeat some of this that we learned about before. So we are looking at electromagnetic energy. Remember, it travels as a wave, and it is made up of photons. If we look at that wave and the properties of the waveform, we have its amplitude, its height, which is telling us about brightness. So I'm wearing blue right now, and I'm in a relatively bright light, but not really bright, and it has a certain amplitude. If I go out into the sunlight, which is not sunny today, but if I go out into the sunlight and the sun's beating down on it and then it's reflecting, it has a higher amplitude and it appears brighter. So it's the kind of the light that I'm in influences its brightness to a large extent. We have its wavelength, the distance from peak to peak, and that is actually our perception of color or hue, where hue is going to be a better term, and I tend to use color, but I don't mean to, because we're going to end up talking about achromatic colors, or colors that don't have color, basically, or hues. So colors that don't have color but not hues, so they don't have, we're looking at something that's happening across the electromagnetic spectrum, and we don't have these specific kind of wavelengths that we are seeing. We're seeing a bunch of wavelengths, or really all of the wavelengths across the spectrum mixed together. We have purity, or the mix of wavelengths, and I mentioned before when I talked about the waveform, and we looked at a nice perfect sine wave, we don't see those very often in the environment. We see those when we are putting sunlight through a prism, when we are looking at rainbows, the sunlight going through water, and when a scientist creates it on a computer. I'm using a monochromatic light. Otherwise, what we're seeing is mixtures of wavelengths. I'm wearing blue, but it's not a rainbow blue. And so that purity or mix is really gives us our perception of saturation or kind of the richness. I'm going to give some examples here. And I'm going to go back to wavelength in just a second to talk more clearly, hopefully, about the perception of these different waveforms. But if we look back again at our electromagnetic spectrum, that it is ranging, and this flips it around, which is kind of nice after talking about hearing, because if we think about wavelength as being really the opposite of frequency, of how many times per second, right, something is happening when we're talking about frequency, but it is influenced by the wavelength, right? So, and I hope that makes sense. So we're talking about wavelength again, and as wavelength is getting longer, we are getting more towards the red part of the spectrum, or we're going out farther to get longer and longer into infrared, microwave, FM, and then AM. If we're getting shorter, we're getting down from, so we're going from red, orange, yellow, green, shorter and shorter into blue, indigo, violet, in our shortest of what we can see. And again, they usually estimate, I see estimates from 400 nanometers to 700 nanometers. I think I've seen them from 360 nanometers to 680 nanometers, but it's around there, where nanometers are a billionth of a meter, so unfathomably small. And then as we get smaller and smaller, we get into ultraviolet X-rays and gamma rays. And since we're talking about color vision and how we're perceiving these wavelengths, I'll repeat, because I think they're really interspecies differences are really neat and interesting, that we do have some I want to say birds, butterflies, and some fish seeing in the ultraviolet part of the spectrum. We have some fish and snakes are seeing in the infrared, so seeing those longer wavelengths. If we look at, again, going back to our waveform, but now we're doing it, this is kind of what I did for hearing, where I flipped it around. Here's the stimulus, and then how it affects perception. Now we're talking about perception and what part of the stimulus gives us that. So our perceived color or hue comes from the dominant wavelength. And so here I have a nice perfect sine wave, which again, we don't see very often in the environment, where the longer ones are red and the shorter are violet. And this is also showing, so that's how many, we can look at this across time, as that's just something that happens, although light is traveling so quickly that it's not worth talking about time, which is probably why they flip it around. Perceived brightness is the amplitude or the height of that waveform. And then the perceived saturation, they talk about pink as being a desaturated red, but really everything we see is these mixes of wavelengths. And so I've drawn here very poorly wrinkles in the waveform, kind of like what we saw with hearing, except, and you can see they're not being consistent because I can't draw, and that's okay. But so if we have some mix of a shorter wavelength in there, we're going to see we're going to have these little wrinkles. But the dominant, if it's dominant, it's going to be a red color, but it's not going to be rainbow red because of these wrinkles and because of this mix. Another way to visualize this, I'm not sure they've taken it out of the book, and I used to not like it, but the more I see it, the more I think about it, the more I'm like, okay. So becoming more and more saturated, moving to the left, becoming higher and higher amplitude, moving up. So if we take A and we move to the right, we get this kind of desaturated, where they say pink is a desaturated red. If we move down from A, we're getting into as if we're taking that red into a dimmer and dimmer light, where it's going to lose some of its really redness because of the lack of amplitude, if that makes sense. It gets a little bit more browny. It's still red, but it's not as bright. We can describe all of the colors by using terms red, yellow, green, and blue. And so we're going to see that this has been used as some to to give us an idea of how color vision works, because we can talk about orange as a red and yellow mixed together, and like that. And pink is a desaturated red. We can use those four colors, right, or those four terms, and pretty much describe all colors by using modifiers or mixing them together. But we also do have these extra spectral colors, so colors that are not on the spectrum, because they are these real mixes of things that are kind of more like we're mixing two colors together, and we'll talk about color mixing. So when I mix red and blue and I get purple, that purple is not on the spectrum. And I have had someone in my class say, well, what's the difference between violet and purple? And I've given a very scientific kind of explanation of, well, indigo and violet are those really, really short wavelengths, and you can see them in the rainbow, and they are short wavelengths that are sine waves. Or we can get a little farther away from that, and they can be, you know, we can change them and make them desaturated, or make them different mixes. But mixing red and blue gives you purple, and so that is mixing long wavelength information with short wavelength information. We come up with something that's really just not on the spectrum. That's my explanation. And it was funny because this woman next to him they were sitting in the front row, and she rolled her eyes and looked at him, and right as I started talking, she said, they are just different from each other. So for me, if you gave me a color and said, is this violet or purple? I'd be like, I'd have to see two colors to even make a guess. I don't know. But a lot of people it's very clear to them, this is violet, this is purple, and they're just different from each other. But if we're talking about extra spectral colors, another one is brown. So brown is a mixture of several colors of several wavelengths coming together, where we don't really have what we would call a dominant wavelength with little wrinkles in it. We have a mixture of wavelengths, and so it's not on the spectrum. So this is a great place to have my final slide for this first video of, so talking about reflectance is what we've just been talking about, kind of, that these wavelengths, that we're seeing certain wavelengths. So the colors of objects are mostly determined by the wavelengths of the colors that they are reflecting. So we're absorbing certain wavelengths, and we're reflecting certain wavelengths, and the wavelengths that we are reflecting into the eyes, that's what tells us this is the color that I'm going to see. And we have these chromatic colors or hues, as I'm going to try to use that appropriately, but I usually just call them colors. But chromatic colors or hues are when we see some of the wavelengths are reflected more than others. And this is a kind of selective reflection. And we're going to compare that to achromatic colors. So colors achroma, so A is again not really colorful, is what chroma, so not colorful colors. So when this light spectrum is, when it's reflected similarly across that full spectrum. So if we look at this reflectance, these reflectance curves, we can see that if I'm looking at, let's say, a tomato, that is reflecting those long wavelengths and absorbing the short and medium. If I'm looking at something with a yellow pigment, it's going to be reflecting long and some medium wavelengths and absorbing the short. If I look at something that's green, it's going to be reflecting more along in the medium part of the spectrum and really absorbing both the long and the short. And blue pigments are going to be reflecting at the short end of the spectrum and absorbing the medium and long. And we'll see these as we start to do this kind of color mixing, why this is important. But then, so those are the chromatic colors or hues with this selective reflection. And again, we usually don't see a rainbow red, which would be something popping, so we're absorbing everything and just popping up right there at about 650 nanometers. That would be the only thing being reflected. That would be rainbow red. But we're seeing these mixtures. We're reflecting some across the spectrum. Versus the achromatic colors. So if we compare the black, gray, and white papers, right? So the white paper, it's reflecting across the electromagnetic spectrum at about 80 to 90% of all of those wavelengths. If we look at different shades of gray, we're going to move down and down and down. As we get into darker and darker, they're going to be absorbing more of the light and reflecting less. As we get down to black paper, it's again reflecting similarly across the full spectrum, but it's only reflecting about 5 or 10% of the light.